All right, which one of you want to get in my gut first? A fermented, crispy, delicious. Oh, hi. I was just eating some pickles. Hey, those unit cell problems aren't fun. My students don't like them at all. So what we're going to do is a lot more of them until they become familiar. You don't have to like them. Kind of like that person at work. You just got to be familiar with it. You just got to tolerate them. So we're going to do a whole bunch more unit cell problems with density and radius. And it's going to feel just like eating a whole jar of pickles, which actually is going to happen right now. Well, hi again, everybody. Mike here. Probably wondering why I got a bunch of tomatoes out. Well, before we talk in more detail about unit cells of solids, I want to show you where unit cells really come from. It's not some sort of hocus pocus trick. Unit cells come from stacking of layers. They call this packing. And so you got two kinds of layers, and they cause some of the unit cells. So what I've done is I've arranged some tomatoes here in what we would call square layers. Now you'll maybe notice, if you look real close, the square layers have more space in between the atoms than these other kinds of layers, which we'll call hexagonal, whichever way you want to say it. So if you really were going to go take a bunch of marbles, don't do it with tomatoes, you'll bruise them, and you really jammed them together, you won't get squares, you'll get hexagons. But so that kind of explains the trend in how much, how you can fit atoms together more closely. So, all right, now pretend with me. Here comes another couple layers, and they stack right on top of each other. That's where simple cubic comes from. And, you know, if you think about it, if you were a tomato, you're not going to want to stand right up on top of those other two tomatoes. You're going to want to go right there, in the little recesses. And if you use your imagination, you will see that hold on. All right, so if you use your imagination, and you think of another set of layers of atoms coming in and fitting right in the little recesses, and then you think that they do that every other layer in an AB pattern, that's where simple cubic comes from. Simple cubic, of course, gives you double the number of atoms per cube, is a more efficient form of packing. Now I'm going to spare you this, folks. Just trust me. If every third layer or fourth layer of hexagons repeats, you get two kinds of unit cells that are more efficiently packed. You get face-centered cubic, and then you get something that is not cubic called hexagonal. And so just keep in mind that the unit cells are really a function of layers stacking on each other, so they don't just, the cubes aren't creating the lattice. It's the stacking of layers that create the different kinds of unit cells, including things that aren't cubic. So there you go. That's just a little bit of background. Okay, let's continue with an example problem in your book. And man, I like corner atoms are the tastiest. Ironically, it needs some salt. Okay, let's do an example problem. All right, so regards to that example problem, it is asking you to prove if nickel is simple cubic. Now, just for frame of reference, folks, there's only one element that's going to pack as inefficiently as simple cubic. You'll notice this little figure shows simple cubic as a green. That's polonium, which is kind of obscure metal. It's radioactive too. Body-centered cubic, all these ones that are sort of off blue. And here's the thing I want to address for our next problem. Cubic close packing is what produces the face-centered cubic unit cell. So if you see cubic close packing, that means the most efficient form of cubic packing. I hate when there's multiple names for things in science, but that just is code for a face-centered cubic unit cell, like in the example we're going to do next. So you'll notice that the overwhelming majority of the elements are either going to, going to be much more efficiently packed than simple cubic. Quite a few of them are body-centered cubic, and we'll end today doing a body-centered cubic. But let's venture on. In density problem world, we're going to do number 82 in your book, and that is with a problem of platinum and its density, which is a face-centered cubic unit cell. Notice it's a little tan there in that figure. So let's do the platinum problem next. All right, folks, so what I've done is I kind of read these things like they're a computer, like you're a computer. So you just read this, blah, 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 platinum. Now you might want to stop right there and say, hey, platinum, I better get my friend out the periodic table. This is 195.08 grams per mole. That's going to come into play just like it did last time. Unless you had some sort of weird problem where they ask you what the element is. I suppose you could prove that from the density and the radius and knowing what kind of unit cell. Blah, 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 blah. Cubic close packed structure means FCC unit cell, which means 4 atoms per cell. Blah, 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 blah. Radius 1.30 angstroms. Angstrom is weird. It's only a unit of distance, and it's 10 to the minus 10th of a meter. It's about a bond length. That's where that came into play. Okay, next you're going to have to think about the mass part's pretty easy. 4 atoms. We can figure out the mass of 4 atoms from the periodic table and Avogadro's number. Volume's a little trickier with these face-centered cubic unit cell problems. And so if I'm going to go ahead and try to draw this, actually, let me first show you what face-centered cubic looks like if you were to look at it head-on. Notice, that distance should be the same. That's more than 2r, like with simple cubic, so it's a little bit bigger in terms of the numbers of atoms. But we can't define what that length is. We need a cube with a length, call it L. We need to find that. To find the volume, we're going to cube that. Tell you what is defined. There's an R. There's an R. That is 2r. What we have, my friends, is a right triangle. The hypotenuse is 4r. So let me show you a better, more professionally drawn image of that. All right. So are we going to do Pythagorean theorem? Oh, yes, we are. Thought you'd never use that again, did you? So L squared plus L squared equals 4r, quantity, squared. 2L squared equals 16r squared. Divide both sides by 2. L squared equals 8r squared. Let's take a square root of both sides. L equals square root of 8 times r. We got to cube that. That's how we're going to find our volume. Now, folks, look, you could just memorize that. You know the problem with memory? You remember stuff wrong, especially when it's not interesting. 862-9756. That's Julie Franklin's phone number from 1987. I wanted to memorize that. So this stuff is not as, trust me, it's not as cute as Julie Franklin. So she drove a Dodge Dart, by the way. But you know, your memory can be tricky. So if you can recreate this from nothing, your freak out factor won't happen. So, you know, do this a couple times, it'll be etched in your memory deeper. So now we're going to go find the mass No, okay, D equals mass unit cell over volume unit cell. So what we're going to do is we're going to find 4 atoms. Going to find the mass of 4 atoms. This is going to be square root of 8 times r cubed. So let's go work on what I think is the easier part. Lowest hanging fruit is the mass. It always plays out the same time for every kind of unit cell problem. So we're going to go ahead and start with 195.08 grams of platinum is what's in a mole. 1 mole, you see how this is shaken out the same way? 6.02 times 10 to the 23 atoms. Here's what's different. 4 atoms, 1 cell. Grams cancel. Well, this would be grams. Grams don't cancel. Moles cancel. Atoms cancel. We should get grams per cell. All right, so, oh boy, now we're going to get out our scientific calculator. 195.08 times 4 divided by Avogadro's number. Now, let's use your noodle here. This better be a small number. It's 4 atoms. And it is. 1.296 times 10 to the minus 21 grams. Big chunk of the problem's done. All right, folks. Now, here's the thing. R is given to us in angstroms. I like to convert everything to centimeters first, and then cube that. Of course, we're going to have to cube square root of 8 times the radius, but let's get the radius and get it into centimeters cubed. So this will be not V yet because we've got to, let's keep this on the back burner. So 1.38 angstroms. 1 angstrom, 10 to the minus 12, 10, I was still in picometers last time, meters. 1 meter is 10 to the 2 centimeters. And nice thing is this really converts nicely to scientific notation. 1.38 times 10 to the, add those powers of 10 together, minus 8 centimeters equals R. All right. So, and that's kind of somewhat on the order of what the last problem was with polonium. So you'll start to recognize these. V equals square root of 8 times 1.38 times 10 to the minus 3 centimeters. Where'd that come from? Right there. We're going to cube that. Now, square root of 8 is 2.828. So times 1.38. This means this is going to be 3.903, we'll call it. Times 10 to the minus 8 centimeters. Got to cube that, folks. Got to cube it. So, 3.0903 times 10 to the minus 8. Now, I have this y to the x button. You might have to use a caret. You might have a cube button. Y to the x, 3, y to the x. V, 5.946 times 10 to the minus 23. Cool? All right. Think about that. Now we're going to slap those together and find our density. All right. I went ahead and fed those numbers in. Now, I am feeling moderately good about myself. As a matter of fact, what I could do is I could convert this. I could move this to be both powers of 10 to the minus 23. That would be like dividing 129.6 divided by 5.946. And that's 21.796. That's a big density, huh? Now, let's be scientific. Let's be sig fig conscious. I'm going to trim that to 3 digits because the only number I was given was in 3 digits is 21.8. And folks, that is about what the density of platinum is. Platinum is super dense. You know, big density metals, tungsten over 20. Gold is 19.7. So this is one of the densest metals there is. But if you get some weird number, you should be able to talk yourself out of it. Like the density of a metal is between, you know, 1 for sodium, which doesn't even really exist in a solid state in a stable way. Let's say even like lithium, 1 point something, all the way up to 22 for platinum. So that makes sense to me. Tough one, huh? Go try another one. There's another one in there with like calcium or something like that. See if you can reproduce that answer. Okay, let's try a body-centered cubic next. All right, number 83 in the book, and you kind of read along. Beep, beep, beep. Barium, the computer, 137.37 grams per mole. Beep, beep, BCC unit cell. 2 atoms, sorry, that's not, no, I'm going to keep 2 atoms per cell. There's only 1, 2, and 4. Now here's what I think is kind of weird. They just, and actually this isn't weird. Body-centered cubic is such a complex structure to find out what R is. There's 4R from one corner of the cube to the other. So finding L is a huge equation that they just cough up and give it to you. Or what they'll do is they'll just give you the dang L. So what they say is the edge length is 5.025 angstroms. Here, take a look at how body-centered cubic looks. Now I don't really need to draw a cube because I can't really, you know, they just give you L. It's a cube. So I'm going to just take V and put it into centimeters and then I'm going to cube it. So body-centered cubic, they'll just give you L. So when it's so complicated, it's an outrageously difficult problem. They'll just say, okay, you folks are probably not going to be crystallographers for a living. And so I'm going to blow off the whole part where we calculate R because it's not necessary to find out the density. Who cares, right? So here we go. Same old drill. Let's do M. 137.37 grams of barium, 1 mole. 1 mole, 6.02 times 10 to the 23 atoms. 2 atoms. 1 unit cell. See how these are all very kind of similar? The only thing that changes really is what that is, and then that's a 1, 2, or a 4. And we've done every permutation of that now. So quick like a bunny, going to get my calculator out, 137.37. Make sure you're reproducing my numbers too. So divided by 6.02 times 10 to the 23, and we got a mass, it's really small, but it's only 2 atoms, 4.5638 times 10 to the minus 22 grams. Save that for later, folks. I like my L in centimeters first. So let's go ahead and convert 5.025 angstroms into centimeters, just like we did in the last example. 1 angstrom is 10 to the minus 10 meters. 1 meter, 10 to the 2 centimeters. Shakes out the same exact way, just add the powers of 10 together. 5.025 times 10 to the minus 8. That's where that came from. That is L. I need to cube it. That's V. So these are actually a lot easier than the last one. We had to do a Pythagorean theorem and all that jazz. I'm just going to take that number and I'm going to cube it. Make sure whatever calculator you got, make a comment or talk to me if you're not getting the same numbers. It's because you're putting it in your calculator wrong. And I have mastered all calculators except Casio's, which are the bane of my existence. So sorry if you have a Casio, they're just impossible to get used to. Cool? Let's find D. D equals m over v. Oh, we're going to get off so easy this time, and I'll show you why. They both end up being powers of same power of 10. 1.2688 times 10 to the minus 22 centimeters cubed. Let me show you what feels great. What feels great is big feeling of power. Wham, wham. I just have to divide 4.5638 divided by 1.2688. 3.596. Now, I'm not super familiar with barium, but it don't sound that wrong. The only number they gave us had 4 digits. I better trim that to 4 digits. I'm going to round that to 3.597. Folks, you made it. You made it through unit cell boot camp. Next time, we're going to make different size spheres. But you've done all 3 unit cells now. And the only thing that really we haven't covered that I want to challenge you to do is there's some problems that ask you to go backwards. Like, okay, here's the density, here's the mass, what's the radius or what's the edge length? So give one of them a try too. It's just same process, just backwards. Folks, we will see you next time. Stay well, eat your tomatoes. Those are good for you. Unless you have GERD, then they're not GERD. Bye.